Okay, we're back and now we're going to look at reading vectors. Before we looked at drawing vectors, now we're going to look at how to measure vectors that are given to us. So on the Regents you might have to do this, and this is also true if you have to draw a vector. But on the Regents there are some guidelines because obviously not everyone's going to draw the exact same vector. On the Regents you have to be within, I believe it's 0.2 centimeters of the actual length, or the printed, the length that they want you to draw for, and within 2 degrees of the angle. So that's actually a pretty wide range. It takes a little bit of getting used to, but it's totally doable. Okay, so now we're going to practice measuring this vector. First thing I'm going to measure is the magnitude, that's the size. So I'm going to line up 0 on my protractor with the edge of the head of the vector, and I'm going to look and I'm going to measure all the way down back to the origin, and I'm seeing that this vector, I don't know, to me it looks like it's a little bit over 3, but not quite to 3.1 centimeters. Remember, always measure to one place past the smallest markings. So I'm going to read this as, let's say, 3.07 centimeters at, and now I have to find the angle. Only issue with finding the angle is, if you look at that, it runs off the paper. So what I'm going to do is the same little trick, or a similar trick that we did on the front. I'm going to take a blank piece of paper. I'm going to put it under my paper right now, and I'm just going to sketch this vector so it goes farther and onto that other paper. Like so. Now I can measure this vector more confidently. And I see that it's about, I don't know, maybe a tiny bit over 102 degrees. So I'm going to call this 102.1. 102.1 degrees from the positive x-axis. Now again, another way that I could say this, if we consider this is north, west, east, south, I could say something to this effect. 3.07 centimeters at, I don't know, let's say, well, if this is 90 and this whole thing is 102 from east, that's got to be 12.1 degrees to the west of north. So west of north. I could say 3.07 centimeters at 77.9 degrees north of west. I could say something like 3.07 centimeters at 12.1 degrees from the positive y-axis. There's a number of different ways that you can name all these different vectors. Okay, really depends on what the situation is calling for. Okay, let's practice this again. I've got this new vector. I'm going to measure the length. Looks like it's just a little bit over 4.2-ish. Yeah, a little bit over 4.2, not quite to 4.3. I'm going to call this 4.24 centimeters. And now we're going to measure the angle. First thing I'm going to do, I know this is east, I know this is south. Let's measure south of east. So remember our rule last time. Whatever the second, like if I were to want to measure south of east, the second direction is the one I line up the 0 with. So I'm going to line up east with 0, and therefore south gets lined up with 90 degrees on the protractor. I'm not going to extend the vector this time. I'm just going to take another piece of paper, or my extra piece of paper, and extend the line like this, so I don't have to make any new marks. And I see that this is, let me fix this up. Okay, so it's between 18 and 19 degrees. I'm going to call about 18.5 degrees south of east. I could also measure this using the XY chart. In that case, I would be measuring like this. We always measure counterclockwise. If we want to measure clockwise, like if you're saying, why don't you just measure this, then you do have to make that angle negative if you're using the XY chart. So we always try and measure counterclockwise. I know this is 270 and this would be 360, so my answer should be somewhere between those two. 4.24 centimeters at, okay, let's see here. If I measure this, I line this up with 0. I get a little bit over, let's see, a little over 70, little tiny bit over 71. So I'm going to call this at 71.5, oh, no, not 71, excuse me. So it's 71.5 degrees from here, plus the extra 270 from the original x-axis, 270 plus 71.5. 270 plus 71.5 gives me 341.5 degrees from the positive x-axis. Okay? And then last but not least, we have this little tiny vector up here. I'm going to say that's not quite 1.5 centimeters. I'm going to call it 1.48 centimeters. And we need an angle. Once again, this is running off my paper. So what I'm going to do, slide this. Okay, so I'm going to move this down a little bit so we can see. And we're just going to extend the vector up a little bit. There, I keep messing this up. There we go. Okay, so I extend the vector up a little bit. Now I measure where that line hits. Oh, I shouldn't have done that. Let's line these up again. Okay, so... Oh, I knew I shouldn't have moved it. My mistake, everyone. There we go. That looks pretty straight. I measure the angle, and it looks to be just over. Let me center this a little bit better. Looks to be just over 70 degrees. Let's call it like 70.4. So 1.48 centimeters at 70.4 degrees from the positive x-axis. Or another way of saying that, and again, like I said, it's totally situation dependent which way you write this. Okay, both of them are correct. There's pretty much an infinite number of correct solutions. There's also wrong solutions. Don't think you can just write anything, but this would also be acceptable. 1.48 centimeters at 70.4 degrees north of east, if this is north and this is east. Okay, so measuring vectors, not all that hard. You might have to use like a second sheet of paper sometimes if the vector runs off, but usually you don't have to. Okay, so we've done measuring vectors. Now we're going to move on to how to add vectors together, head to tail. This is important because if you think back to our original example that we were looking at, let me move this up so we can see. If you think back to our original example for why we were studying vectors in the first place, it was the hiker who hiked to the north and then the east and then the south. The hiker had hiked 15 kilometers, but was only 5 kilometers away from where he started. And that happens because the hiker was changing directions. You can't just add the magnitudes of those vectors up and get how far the hiker is away from where they started, because if vectors are in different directions, you can't just add them like normal numbers. It doesn't work. Okay, and we saw that it doesn't work in that first example. Because it doesn't work, we've come up with different methods for figuring out graphically how to, and this whole process is called adding vectors together. So if you have something, if you have a case where you have to add vectors together, we figured out this process to do that so that you can get a correct answer. And why you would need to do that, again, you want to, like in this length case, you want to make sure that you have the right, that you know how far away the hiker is from where he started. Just adding the magnitudes, it just doesn't work. So we have these methods. You're going to learn 3 of them for adding vectors head to tail when you have a situation like this. This is called adding vectors. Your example here, an ant walks 6 centimeters at 35 degrees west of north and then 9.4 centimeters, 28 degrees south of east. Determine how much distance the ant... Oh, that's a little blurry, isn't it? Determine how much distance the ant has traveled as well as its displacement from its starting point. So what I'm going to do here is I'm going to give you the steps for doing something like this in addition to actually doing those steps. So up top right here, we're going to write down those steps. The very first step in a case like this is just to draw the first vector that you're given like normal. So we're told the ant walks 6 centimeters, 35 degrees west of north from the origin. So I'm going to put my protractor down. West of north means that I start my protractor being lined up towards the west and I measure to the north of that. So my protractor should look like this, 35 degrees. I'm going to go make a little mark right there. There's 35. And then 6 centimeters along this line. go. There's 6 centimeters. Draw back down. Okay, there's my first vector. Everything's fine. The second step is where you got to be a little careful. Now, from this step on, every other vector that you draw will begins at the head of the previous vector. So we've drawn the first part of the ant's motion. Imagine the ant stopped there. It then says he goes 9.4 centimeters at 28 degrees south of east. So what that means is we need to draw the next vector to show the next phase of his motion, but we're going to start it from right here. In order to do that, it kind of makes sense, therefore, that anytime you do this, you draw a new compass rose each time so that you can get an accurate direction. And it is really important, actually, that you get this right, okay, that you draw an accurate compass rose. That compass rose is going to be centered on the spot where the last vector left off. So that's going to be right here. Okay. You don't have to do it really fancy. Just make sure that the vertical line is parallel to your original vertical line. The horizontal line is parallel to your original horizontal line. If they're tilted, then you're going to get bad results because then your angles are going to be all out of whack. Okay, there we go. There's my new compass rose. And now I need to measure 28 degrees south of east for 9.4 centimeters. South of east tells me that east should be where I line up 0, and south should be where I line up 90. That's got to look like this. 28 degrees to the south of east means start at 0, go to 28. That's right about there. 9.4 centimeters. Oh no, I have drawn this first vector totally wrong. Wow. West of north. That's embarrassing. 35 degrees west of north means we need to start like this. West of north. There we go. 6 centimeters. So in case you haven't caught on, the reason I just scribbled that out is because when I drew this the first time, I either was not thinking or I misread this as north of west instead of west of north. The order literally matters. The first direction, or the west, is where I should be lining 90 up with. North is where I should be lining 0 up with. To the west of north means start at north, measure 35 degrees to the west. That vector, even though it doesn't look that different, should look like that instead. Oh, that's so embarrassing. I apologize, everyone. I'll make sure to put a note about this in the video. Okay. Now, 28 degrees south of east. This one I had all set up right, but I was starting from the wrong spot. There we go. That makes more sense. 9.4 centimeters. Okay, so if you do notice that you were off with something, not bad thing, I mean, you can always go and fix it, but that's why you want to check your work before you draw, because it's very easy, as you guys have seen, to make a mistake with vector addition since you are drawing like this. Okay. In any case, you're now seeing why we're doing certain things. So now we have the first part of the ant's motion, as the ant goes from the origin up to 6 centimeters away at 35 degrees west of north. Then the ant walks this way. So what we've done is we've kind of traced out the motion that the ant has gone through so far. The question here is determine the distance that the ant has traveled as well as its displacement. And before I actually do that, I'll find the distance in just a second, but I just want to make a note. If there were other vectors, I would then just continue them from where my last vector left off. So if there was another vector, I would make another compass rose here and then draw that next vector. You keep drawing new compass roses in the next vectors until you run out of your list of vectors to draw. As far as the distance, that's just the total path length. We know this is 6 centimeters. We know this is 9.4 centimeters. The distance, therefore, is 6 centimeters plus 9.4 centimeters, which is 15.4 centimeters. The ant has walked 15.4 centimeters in total. But that doesn't answer how far the ant is from its starting point. Okay, that doesn't answer that. So what we need to do is we need to figure out how far away the ant is from here. We can do that by drawing a last vector. That last vector's name is the resultant. The resultant vector is also known as the sum of all of the added vectors. We've put down all of our vectors that the ant walked on this map. So in essence, what we've done is we've added them all together. We're finding the resultant vector now. What ultimately happened? Where did the ant start and where did he end up? The resultant goes from the origin, or in other words, the tail of the first vector, to the head of the last vector. Okay, from the origin to the head. So that means to draw in the resultant, we would just draw this. And I'm going to make it a little bit darker so that it stands out. Or I'm going to try to at least. The resultant still gets an arrowhead. And I'm even going to label it with resultant. Okay. And we can measure the resultant. We can measure the magnitude. This seems to be about 4.7, 4.8, somewhere in there. I'm going to say that the resultant, which in this case is the displacement, is 4.75 centimeters at, and now we're going to, well, actually first we're going to extend this line out a little bit so that it'll show up on the protractor. Okay, that looks like at about 4.1 degrees from, let's see, or no, since we're doing a compass rose, this is east, this is north. It's 4.1, a tiny little bit degrees north of east. Okay, so there's my resultant. Again, what that is the sum of all the vectors. Really what it shows us is how the overall motion of the ant. From beginning to end, the ant ended up 4.75 centimeters away in the direction 4.1 degrees to the north of east. That's what a resultant shows us. Since these are length vectors, it shows us the displacement, which again is defined as the straight line path from the starting point to the ending point. If these were not length vectors, let's say if they were force vectors or velocity vectors or acceleration vectors, the resultant would not show us a displacement, it would show us something else. The other thing that would have to be done is there'd have to be some sort of scale used in order to translate from how big the force is or how much the object is accelerating to a length on this paper. The only other thing that might show up on a vector addition problem is drawing in or a reference to something called the equilibrant. The equilibrant is a vector that has the same magnitude as the resultant, but it has the opposite direction. And by opposite, I mean exactly 180 degrees opposite. So I can show that. If I was asked to show the equilibrant here, I would flip my protractor around. If the resultant was at 4.1 degrees north of east, then the equilibrant should be 180 degrees opposite that. That would work out to 4.1 degrees south of west. Or if we're doing 4.1 degrees from the positive x-axis, it would end up being 184 degrees from the positive x-axis. So let's see, it would line up with about here, and it would be 4.75 centimeters So let's see here. There we go. Okay. Something that looks approximately like that. Notice how the equilibrant is the exact same size as the resultant, but it's in the exact opposite direction. The reason you might need an equilibrant, the technical definition for why it's important and why we even talk about it, is it's the vector that you would use, that you would add to the resultant to bring the new resultant back to zero. For instance, I mean, on this diagram with the ant would have to walk over a vector that is equal to the equilibrant in order to get back to its starting point, the origin. That's why we talk about it. Okay, so this is how to add vectors. It's not adding in the sense that you've always added before with numbers. Adding vectors means, in this case, literally tracing out the vectors and finding the resultant. Okay, and in some cases, we're going to have to add vectors together for some purpose. If they're length vectors, then we add them together to find, let's say, a displacement for an object. How far is the object and in what direction from where it started? We do that by doing head-to-tail vector addition and finding the resultant, which tells us the displacement. It tells us how far away the object is from where it started. And sometimes you might have to know about the equilibrant. That's pretty much it. Some of the stuff on the homework here is it just is asking you to either draw or measure vectors, but there is some stuff on there as well about adding vectors together. These are the steps. This is all you'll ever going to have to need. Oh, I didn't even write in my equilibrant measurements. It would be 4.75 centimeters at 4.1 degrees south of west. Sorry about that. In any case, all you need, all the steps to add vectors together are listed right here. If you can follow these steps, then you should be fine in terms of adding vectors together. That being said, if you do need help, obviously, please let me know. It's a little bit of a tricky topic until you get the hang of it. We're getting close to the end of our little mini math unit. I think next we'll be talking about making and reading a graph. Again, let me know if you have any questions, and good job. I will see you soon. Bye.